Hello guys, welcome once more to another video in our YouTube channel. So in this video we are going to be looking at equation under motion in a resistive medium. The equation reads: a particle of mass m falls from rest under gravity in a medium in which resistance to its motion is mkv, where k is a constant and v is the speed of the particle. Write down the equation of motion of this particle. If the motion were to continue indefinitely, v will approach a constant value capital V. Show that k is equal to g on capital V. Hence, show that dv by dt is equal to g on v into v minus v. Sorry, here is g on capital V, not small v. Okay, next, show that the particle is moving with velocity capital V on 2 after time v on g ln 2. Show also that during this time the particle has fallen a distance s given by v on g into ln 2 minus half. Alright, so the first thing I'll tell you guys is that if your device doesn't show this video very clear, you make sure you adjust your YouTube resolution. So you just increase your resolution by going to the settings and then choosing a specific resolution which is more than the current resolution. But if you're seeing the video clearly, then it's fine. Alright, so the first thing to do is that they say we should write down the equation of motion of this particle. So I'm going to draw and we display how the particle is moving. Okay, so we have the particle is falling from rest under gravity in a medium whose resistance is this. So I'm just going to call the particle maybe a ball. So we have a ball, right? It is falling from rest. Okay, now I'll just indicate the forces acting on it. You have the weight which is acting from the center going downwards. We have the weight of the particle, and then since it is in a medium whose resistance is mkv and it is going downward, so let me first of all indicate the direction of motion. So this big arrow here indicates the direction of the acceleration, or the direction of motion is going downwards. Since it is going downwards and we have a resistive force, then you have the resistive force resisting the motion, so pointing in the opposite direction to the motion. Okay, so we need to indicate the magnitude of those forces. We have the weight which is capital M times g. G is the acceleration due to gravity of the particle. We have mg here, and then the resistive force is mkv as it was given. So we have our resistive force to be mkv. We are being told that m is a mass, k is a constant, and v is the speed of our particle. Alright, so this is what is happening. Now what we need to do is that we need to use the Newton's second law of motion. So from the Newton's second law of motion, we know that the net force acting on that particle is equal to the mass times the acceleration. So from Newton's second law of motion, we have that the net force, I can call it Rn, should be equal to the mass of the particle times its acceleration. But what is the net force? It's simply the sum of the algebraic sum of the forces in this system. Okay, so I'm going to consider that the downward direction according to my reference frame. So I'm going to say all forces in the direction of motion are positive. So downward is positive. So that's my reference frame. Downward is positive and then upward is negative. So the net force acting on this particle is positive of the weight, which is mg, plus negative of mkv, right? Because I'm taking the algebraic sum, meaning I take the sum together with the signs. Since mg is going downwards, I call it positive, plus mkv is in the opposite direction to my reference frame, so it becomes negative, equal to ma. Alright, so it means that our m can cancel all through, right? Because m is common in this term, m is common in this term, and m is common in this term. So m cancels and we get g minus kv to be equal to a. Okay, now our A is simply dv by dt, so dv by dt is equal to g minus kv. So this is the equation of motion of our particle. Let us put in a box. So this is the equation of motion of our particle. Okay, now the next question is asking us to, we have an information that's been given to us. Here is the information. It says that if the motion were to continue indefinitely, our speed will approach a constant value of capital V. We need to show that k is equal to this. Okay, so we give our statement. So we have, when our V is equal to capital V, then what happens? Our acceleration is equal to 0 because the velocity is constant. But why is it so? Let me just give a little explanation to this. We know that the acceleration of a particle is simply dv by dt. Okay, but we know that when v is constant, then what is dv by dt is simply 0 because we are differentiating a constant. Okay, so when it arrives a constant value capital V, then the acceleration is 0. So that's a little explanation. So from there we can see that our dv by dt is equal to 0, means that we come here and we have g minus kv, but in the place of v I'm going to replace it with capital V. Okay, equal to 0. Okay, so we can have our k times capital V to be equal to g, this is small k, and then what can we conclude? We can conclude that our k is equal to g divided by capital V. We have proven that. Let me highlight it by putting it in a box so we know that we have proven that. Okay, now what is the next question? Hence, still in the same question, show that dv by dt is equal to this. Okay, so after having our k, we just need to come back to our equation and replace k. So since our k is equal to g over capital V, we have that word, that dv by dt will be equal to, since it is g minus kv, it becomes g, which is g minus, now what is k? K is g divided by capital V, then times v. Okay, because that is what we have in our formula. Now from here we are going to get, we can factor out the g, and then we have 1 minus v over capital V. We can look for the LCM and then we arrive at the proof immediately. So our dv by dt will be equal to g divided by capital V into capital V minus small v. Okay, so that's what we have. Okay, so we have also succeeded in this. Now the next question, show that the particle is moving with a velocity of v divided by 2 after time v divided by 2 times ln 2. So we need to first of all get the velocity at time t seconds, then we replace t with v over g ln 2 and we verify if the answer is v divided by 2. And how do we get the velocity at time g? So we have to get the speed at time t seconds. Okay, so we need to integrate our equation. So dv by dt is equal to g divided by into v minus v. I'm going to separate variables and integrate both sides. Okay, so it means that dv divided by, I'm going to just divide both sides by this quantity. So divided by this quantity is equal to, and then I'm going to send dt to the right hand side. So I'm just going to allow my G on V here. Remember that capital V is a constant, but this small v here is the variable which is changing. The capital V is a constant value, maybe 2, 3 or whatsoever. So we have this, then we multiply it with dt. Now since I have separated variables, I can now integrate. I integrate both sides. I have dv divided by capital V minus small v to be equal to g divided by capital V times the integral of dt. So what does it mean? If I integrate the left hand side, I'm going to get negative the ln of v of capital V minus small v equal to, I integrate the right hand side, I have g on capital V times t, then I need to add my constant of integration, maybe c. Okay, now I use my initial conditions to get my constant of integration. Please, if you don't understand, if you didn't understand how I integrated this side, give your comment in the comment section. Okay, now we know that initially the particle was at rest. What does this mean? It means that when your initial velocity is 0, it means that when your time was 0, your initial velocity was 0. Let's go back to the equation. A particle falls from rest. Okay, alright. Now having this in mind, we are going to get, so what we're going to do is that we need to get our constant of integration c, and from that equation our c is equal to negative this minus this quantity here. Okay, now so it means that when c equal to 0, our v is equal to 0. So I just need to come and replace 0 here, and I replace t with 0. This term becomes 0, this term just becomes v, so that is my c. So having c to be this, so I can just put it up here. So this implies that c is equal to that. Now from there I can get negative ln of, or you just come here and you replace the value of c, and then you bring like terms together. So we have our c is negative the ln of v. I can add this guy on both sides of the equation, and then doing that I'm going to get that the negative, anyways, the ln of v minus the ln of the absolute value of v minus small v is equal to g divided by capital V times t. Okay, now the law of logarithm, I can bring the two logarithms together. So I have the ln of, now since I am subtracting and the lns are logarithm to the base e, they have the same base, I just need to divide their arguments. So I have v divided by v minus v to be equal to g divided by t times t. Okay, now we're told that we need to show that when the time, that the velocity is equal to this when the time is this. So I'm going to replace the time by that, and then I show that the velocity is that. So next, when my time is equal to that, so when my time is equal to this, what is the value of v? What is v? So I go to my expression above and then I look for v. Okay, that's, we're actually proving that v is equal to something. So it means that this guy here, all of this will be equal to g divided by v times my t. This is my t, I just replace it with its equivalent. So you have all of this. Okay, now the first thing to do is that the v is going to cancel here, so it's not going to be there. You just have 2, because I was already wondering why we are having 2 to the power g, because this g here we cancel with this g here. Sorry for the delayance. Okay, now taking exponential on both sides, we can cross multiply. So it means that if you cross multiply, you are going to get v to be equal to 2 times v minus small v, where we need small v. Okay, so that minus 2 small v, sorry, because the 2 also multiplies. So automatically we have our small v to be capital V divided by 2. We have proven that. So let us conclude that this is okay. Alright, now we have the last part of the equation, which is saying that we should show also that during this time the particle has felt a distance of s given by what you can see. Okay, so we are showing that s is equal to this. So we are going to come back to our differential equation, which is this guy here, and we rewrite it. So our dv by dt, okay, or in fact our dv by dt is equal to this. We are going to use that. Okay, sorry for that. Alright, so our dv by dt is equal to this, but we saw that it was actually g on capital V into capital V minus small v. That's what we saw. Okay, now since we need distance, remember that dv by dt is just the acceleration, right? So we are going to derive a new relationship between the acceleration and the distance. Okay, so we know that acceleration is simply dv by dt. Okay, but if we have the distance and we call the distance to be x, for example, then we know that our velocity is equal to dx by dt, where x is our distance. So with that said, what do we have? We have that our acceleration will be the dv, there will be the d of dx by dt, because this guy here is simply our v. Then we need to divide by dt, okay, which is in the denominator. We divide by dt. Okay, so this will give us d squared x by dt squared. Okay, so this is the first thing we need to note, though we are not going to use it, but you have to just note it. Okay, now we want to get a relationship between the acceleration and the velocity alongside the distance without time involved. Okay, so we have acceleration to be equal to velocity divided by time taken, or let me just put the dv by dt. Okay, now we need to eliminate time. Okay, and we know that the velocity is equal to dx by dt. So from this second equation, what do we get as dt? It's simply dx divided by the velocity. Okay, so we fit in the first equation and we get the acceleration to be dv divided by our dt is what? Dx divided by v. The v goes to the numerator and we get v dv divided by dx. So this is what relates the acceleration with the velocity alongside the distance. That is what we are going to use. So we are going to replace that value of v here. We are going to replace the value of the acceleration here, this, and then we change the variables and we integrate as well. Okay, so let us write on. So acceleration equal to g divided by v minus v. Okay, we have alright, so our acceleration being equal to this, it means that we replace it with v dv by dx, v dv by dx to be equal to g divided by v times v minus v. So we can separate variables and we integrate. So I'll have v dv divided by this quantity to be equal to g divided by v times dx. Okay, so this means that we can easily integrate both sides since we have separated our variables. So the integral of v dv divided by v minus v is equal to the integral of dx, and then we have our constant outside. Our constant is g divided by v. Okay, now remember that x is just a distance. Okay, now how do we integrate v dv on v minus v? So firstly, we are going to rewrite it. That's, we need to do partial fractions, but I'm going to do it in an easy way. So v divided by capital V minus small v can be written as negative into v divided by v minus v. Okay, now it all depends on you. You can either do your partial fractions, or that is via long division, or you do what I'm about to do. So I'm going to make the denominator to be in the numerator. So I'm going to write my denominator first, which is v minus capital V, and then for me to have v minus capital V to be equal to small v, it means I need to add capital V as well. I need to add capital V because capital V minus itself is plus itself is 0. Then I divide by v minus capital V. Okay, so I now call this quantity one quantity divided by this quantity will give me 1. Then plus, we now have v divided by small v minus capital V. Okay, so even if you did long division, you arrive at the same answer. So we can just distribute back the negative. So it means that this integral is just equal to the integral of, alright, so it is equal to the integral. I can distribute the negative signs there. I have negative 1 minus v divided by, or I can say just say plus v divided by, now I just send a negative sign here. Okay, so I get v minus v. I'm integrating with respect to v, small v, and this is equal to what? G divided by capital V times x plus a constant of integration. Maybe we can say r. Okay, because we integrate the x, we have x. Alright, now what does this mean? It means that if we integrate negative 1, we get negative v. If we integrate this, okay, integrating this, we just have our negative capital V, the ln, negative capital V, the ln of capital V minus v equal to g divided by v plus r times x. Alright, now we need to look for r, and we know that initially at t equal to, or at v equal to 0, our x is equal to 0. Okay, that's initially. So it means that our arrow will be equal to, our v is 0, so we have v being 0 there. We just have negative v ln v, negative v, the ln of v, of capital V as well, to be equal to g divided by v times x. G divided by v. Our x is 0. Okay, sorry, we just have to subtract minus this because we need arrow. So we are going to get this quantity here is 0, so we just get this. Okay, now let's see if everything is okay. Alright, let's just see if everything is okay. Let us look back at this division. Here you have 0, your negative sign is outside. If you multiply this with this, you just get this. We add this, you get this. Okay, so yes, when you integrate this, you get v. Then your v is a constant. Integrating just this will be negative the ln of that. Okay, so we are okay. So it means that our we just copy this right and replace the value of arrow with its identity, and then we see what we get. So it means that our arrow is negative v the ln of v. That's it. Okay, now we have to show that, let's see what we are showing. During this time taken above, you have fallen a distance of this. Okay, so we need to replace the velocity with this guy, because after this time taken, that's the velocity that we have. Alright, so we need to replace it with v on 2. Okay, and we replace our x with s. So this means that our v on 2, then we need to put a negative sign in front of it, minus capital V times the ln of capital V minus capital V on 2. We are replacing small v with v on 2. Let me write so you get it. Replace v with v on 2. So to be equal to and we replace x with s, the distance. So this we just have it, we replace s with s. Okay, now what do we have? It means that we have negative v on 2 minus v. Now v on 2 minus v on 2 is v on 2, then equal to g on v times s minus v ln v. Okay, so we need to bring the like terms together. So we have minus v on 2 minus v on 2 minus v on 2 minus, so if I bring this one to this side, it's going to be plus v times the ln of v, then minus v times the ln of v on 2 to be equal to g on v times s. Okay, so this means that it means that we have minus v on 2. Now you have here, we can write this down as v into ln v minus ln 2, v into ln v minus ln 2. Okay, now we have v minus v ln v, that is v ln v is 0, and we have minus times plus ln 2 is ln 2. So we have, but there's a v multiplying it, so here is plus v times ln 2 to be equal to g divided by v times s. Okay, so this means that our s is equal to, we can factor out, remember we multiply all through by v, we factor out, anyways, let me just write g on v. Okay, now on the left hand side now, which is now our right hand side, we have a v factored out into minus half. Okay, so it means that our s is equal to v squared divided by g into minus half. So here is supposed to be v squared, so there's v squared. Alright, so that is it about the equation. So if you love the video, make sure you like the video, share the video with your friends, teachers,